Let me begin the class. So we will resume from the commodity and other asset presentations that we were doing on Wednesday. So let me share my screen. Right. So can you all see the slides?
Yes, sir.
Yes,
sir.
Yes, sir.
So these are the agricultural commodities that we were discussing on Wednesday. I hope you have visited the commodity exchange websites, both the National Commodity Exchange as well as the MCX. And you can see a lot of things there, which I have listed here, but there are some other things also which are not usually available in the Indian markets, but are available in the US or Australian market or some other European market. So you can see something like even frozen orange juice can be a commodity. So typically all agricultural commodities has a seasonality because it depends on agricultural cycles. So there are some mean reversion in prices. So there is a kind of up and down movement which comes back to an annual average price. And the farmers typically use this pattern, if they are informed about it, to choose which commodities to produce in which season and how much land to use for a particular commodity. And of course, as I already showed you, weather is a very important factor here. So the commodity exchanges also track the weather very closely. The other commodity market, in fact, a very, very big commodity market is involved with metals, deals with precious metals like gold, silver, platinum, all these things, and also deals with industrial metals like copper, tin, lead, zinc, nickel, aluminum, etc. This is also a very big market, and if you again go to the National Commodity Exchange or MCX, you will get to see a lot of metal commodity contracts available there. Seasonality is no longer important, but what is very important is the production cycle for metals and the production cycle for users of metals. So it could be large construction companies, it could be engineering firms who uses a lot of these metals as input, and the production of such metals and how much investment is being made in mining, because mining is the source, primary source of this metal. Of course, it is processed through the different chemical processes in the steel plants. But that's a different story. But what we really need to understand is the metal market is typically controlled by the mining activity intensity and on the other side, the use of metals intensity. Of course, some recycling is possible. So the actual amount of commodity available for use is slightly more than the production, because some of the older production comes back after recycling. Energy commodities, we were talking about Nord Pool on Wednesday, and also the other website that I started to show you, which is the Indian website. But I said that it is not very informative, but it has some information here. If you can see my screen, the Indian Energy Exchange, which is a new one. And here they are looking at finite time blocks of energy. So it could be 15 minutes, 1 hour, 1 day, like that. And the delivery period is usually a short time. It's today or tomorrow mostly. So if I just update it here for tomorrow, oh, it is not available. Okay. So this website is not yet absolutely ready. So some of the data and reports are not easily accessible, but this is the Indian market, new one, so it is worth looking at. And if you want to know what are the products, you can go here. For instance, you can look at the day ahead market. Day ahead market is like 1 day in advance. So if I scroll down here, This is the day ahead market. And here you can see the purchase bids, the sell bids. These are all in megawatt hours. And how much volume is there in the market. These things are mentioned on this left panel. There are some press release and other stuff. Sorry, on the right panel. And you can scroll for data here. There is some data available in the market data section, and you can look at the other products in the product section. So that is something for you to browse through and get yourself familiar with, because as I said, unlike typical stocks and bonds, which are absolutely paper kind of assets, these assets have physical connotations, agricultural, metal, energy, these things. So it is important to know how these physical characteristics are.
ITX, transforming India's gas market with IGX.
What have I done?
Changing the dynamics of gas-based industries. Promoting.
Let me close this one because some video is starting and which I cannot stop. Okay, so are you with me so far?
Yes.
Yes, sir.
Yes, sir.
Yes, sir.
So now let me continue with the other commodities that I want to mention here. So we were talking about energy, and energy is primarily oil, gas, and electricity. Oil, very big. Gas and electricity also becoming bigger and bigger because now we have better and better technology to store such energy. And again, if you look at the price trends, you will see that they all have this mean reversion characteristic, which we will discuss in mathematical terms later on when we are learning about the models. But if you have studied a little bit of stationary time series, then you will know that a stationary time series is characterized by a constant mean, time independent mean. So even if the process moves away, there will be typically a tendency for it to be, move around a particular constant mean. So that as a mathematical model is a mean reversion process. So have you done that time series? What I mentioned, the stationarity and other things?
No, sir.
Okay. So anyway, you will be doing it this term, right? Your time series class will start this week, right?
Yes.
Yeah. So many of the time series features we will be talking about when we talk about how to price financial products, because all financial data is after all time series data. So all the time series model techniques will come in useful. Okay. So we will keep referring to that. And in addition, gas and electricity in particular, they also exhibit jumps. Now, these jumps is something that we need to understand in a separate manner, because so far we have not talked about how the price moves. In general, we assume that the price moves in a smooth manner. So for any small interval of time, the change is also very small, which sort of matches with our idea of infinitesimals. But some products prices do not have this feature. They sometimes exhibit quantum jumps, and then it becomes harder to model such price processes. So at some point we will be having some special lectures by other experts who will talk about these jump processes and how they are used in modeling some of these financial assets. Okay, so as I said, oil is very big. So the largest commodity market in the world is that of crude oil. Crude oil means the oil that comes out of the mining operations, the oil rigs. The primary source of oil are the oil rigs. So these are called the crude oil. Of course, there are many classifications, many grades, like Brent crude, which is from the North Sea. Then there is this West Texas crude, which comes from Texas, and so on. Texas oil rigs. In fact, Bombay High is an oil rig that is run by the ONGC. You know about Bombay High, correct?
Yes.
And once you refine crude oil, it gives you many different types of products. So gasoline is one product which is used to run cars, heating oil, kerosene, and also Vaseline. Did you know Vaseline is a byproduct?
Yes.
Yeah,
Yes, sir.
Vaseline that we use on our face, that's a byproduct. So anyway, that's a smaller market, but these markets are really, really big. So the crude oil is the largest commodity market in the world. And we spend a lot of time studying oil prices or prices of contracts written on oil. There are many such contracts. Oil derivatives are available virtually everywhere. So it is just like derivative contracts on stocks. Huh? Oil contracts are also available almost everywhere because it's so important. And some major examples are like the futures and futures options, which are available in the New York Exchange, New York Mercantile Exchange. And there is also an international petroleum exchange. These are big markets, and all sorts of derivative contracts on oil are available for trade. Natural gas and electricity is relatively more deregulated, so there is not so much structure there. And slowly,
Sir, what are futures?
yes.
What are futures?
Oh, that's where the price for a future date transaction is fixed today. So if I want
Okay.
a transaction 3 months later, I can fix the price today. That's a futures contract. We will talk about contracts. We haven't yet started talking about normal contracts, but I just wanted to lay of the land, the things that are involved. Some of the terms here might be unfamiliar, but just hold on to them and we will come back there. So slowly the gas and electricity are coming out of government control. You know, in our country, Reliance has now become the largest energy producer. Earlier it was all government of India, but now Reliance has, overtaken. So it is becoming more privatized. And those who are the suppliers of this energy and those who are actual producers, they are not necessarily the same people. So those who are actually running the oil rigs and those who are actually operating the market, this could be different entities. So there is also another layer of transaction there. Okay, so it's like you go to a mine and you buy the crude metal, then you bring it to the market, and while you are bringing it to the market, you are adding some value to this, because otherwise people would not be able to access that crude metal. So I am the supplier, I am not the producer. The producer is actually in the mining operation. So these might be separate people. Natural gas derivatives, just an example. So a typical contract, what does it specify? It will specify delivery of a specified amount of natural gas at a roughly uniform rate to a particular location during the month. So basically I will buy a contract which will give me, say, 1,000 cubic meter of natural gas every day for the next 30 days. And this kind of contracts are measured in British thermal units, BTU, and a typical contract would specify a very large amount of such units, like 10,000 million. So as I said earlier, that most of the commodity trading is done by large companies. So it is not really for small retail traders or investors, because all of these are traded in very large amounts. Any questions? So if you have questions, just stop me. We will discuss. Otherwise, I will assume that it's fine. Okay. Similarly, we have electricity derivatives. Most interesting market is the United States. United States is divided into 140 different areas. So, and in each of these areas, the electricity market is created for trading. So there are auctions that goes on here for the operating of this market. So it's a very interesting operation. It is just like our telecom block operation. By the way, last time I said that you should look up telecom and coal block. Did any of you see? So I asked you to look up coal block auction on and telecom spectrum auctions. In particular, we mentioned about this 2G spectrum auction scam. Has anyone looked it up? So it is terribly quiet now, but again, so whenever we discuss things, it is good to look things up, because these are not only for general knowledge, these are also related to what you are studying. It helps you to understand why certain markets operate in certain ways. Are you with me there? Can you all hear me?
Yes, sir.
Yeah.
Yes, yes.
Yeah, but I would be happy if some of you actually look these things up and we can talk about them, because these are important financial market events, and it helps us to understand how the financial markets operate. In fact, why certain rules change. The rules change because of certain events. So it is good to know about events. All right, so I will hope that we will take a look at these things this week and we can discuss it later on. So let me continue with my presentation then. So, okay, so electricity derivatives, we were talking about the United States market. This is one of the more organized markets in different, separated into different control areas and different auctions happening and so on. Again, this is example of typical contracts. So you receive a number of megawatt hours at a particular location. And this could be daily or monthly, and different kinds of contracts can be written on that. Again, there is a new term here like swing option, which we will talk about later on. But these are particular type of derivative contracts specifically designed to deal with the electricity product. Commodity prices, particularly in terms of future contracts, because future contracts are actually the most common commodity price contracts. They are used most often. They are used to define in what is called a risk neutral world. So when we start the formal modeling today, our main target will be to understand what is this risk neutral world or a risk neutral probability, and how to price things using that risk neutral probability feature. In any of these models, we can build in other characteristics like a mean reversion characteristic or a jump characteristic. One example is given in chapter 32 of Hull's book, which uses the mean reversion for constructing a trinomial tree model for commodity prices. So this kind of models would be our final targets. So once we are able to build up the formal structure, the definitions, and understand some of the basic tenets, basic principles of the financial market, we will be building up this kind of models. Weather derivatives, just a little bit, because it's a slightly different thing from the others. Examples are like heating degree days and cooling degree days. So these are very common in some of the Nordic countries and also in Canada, where the climate is typically very cold. But there are certain agricultural products which requires a minimum temperature to thrive. One big example is wine growing from grapes. So the grapes that are used to make wine needs a minimum temperature for a sustained number of days to actually thrive. Otherwise, they will get blighted and the produce will be no good. And this is very big money, because the wine growing grapes industry or agriculture is a huge money making venture. So the farmers who run such wineries or grapevines, they will buy this kind of weather derivatives as an insurance against bad climate or bad weather. So they would want a minimum number of sunny days or some above some critical minimum temperature days. If they don't get it and they have bought this derivative, then they will get compensated by the derivative contract seller, which is the exchange in this case. Is this clear?
So then how is it different from insurance? Like,
It is not very different from insurance. It is very similar to it. Most of the weather derivatives are actually for insurance purpose only. But if you look at these contracts, you can see that you can also use them for profit making. You can try to buy and sell this kind of contracts to make profit. That is possible. But actually for the farmers, this is an insurance contract, but a very specific insurance. Because you see, typically our insurance is on final assets, final goods. So if the final good gets spoiled, you get back the valuation of the final good. But here, the farmers are insuring themselves against the natural phenomenon that will eventually reduce the value of their final good. The final good will never come to the market because the grapes will be blighted, so no wine will be produced at all. So their contract is based on what is observable. Because the product is not going to the market eventually, the price will never be observed. But what will be observable is the input. And here the input, relevant input is the temperature. So they are buying insurance against temperature. Is it okay?
yes, sir.
So I mentioned this in particular because this is slightly different from the other financial products. And also because this is a very, very specific use of financial techniques, financial modeling techniques, and also a very, very interesting use of probability. Because you see, whenever you want to calculate a price, you have to calculate the expected value, variance, and all those things. And for that, you will need to first figure out what is the correct probability distribution. And in this context, figuring out this correct probability distribution is a very interesting exercise. So I'll finish with this weather derivatives here. Typically, we write forward contracts or option contracts on weather derivatives. And as I said, primary application of that is insurance. All right. So we are more or less good to go. Before I move to my notes, there is a nice wiki page on weather derivatives, which I am now showing you on screen. Can you see this?
Yes, sir.
This wiki page is not bad. It's pretty good. There is some historical facts here which you can read up, and there are also certain references here. You see in this part, see also, there are some documentation on weather risk management and some companies, how they do it. So that might be an interesting thing to look at. What are the techniques involved here? What are the historical concerns? What is the structure of the market? Like, I mean, the nature of the buyers, who are the buyers? So those things you can understand better. And as I said, this is just not just for general knowledge. This is actually to understand your model better or build up a better model. So this is where I will, stop the description of the market. So this slides can go. And if you want to ask me something, you can ask, or we will begin with our formal definition now. So do you want to ask me anything at this point? And of course, I'm going to ask you again to look at the websites and read up some of this associated material. it is not possible to discuss everything in detail in class. But if you read these things up, there will be questions and I will be happy to discuss such questions, but only if you are reading things. Okay, all right. So now let us get back to the lecture notes part 1. So we were around here on Wednesday. So now I am going to start from Discuss chapter 1. So if you have the book in front of you, you can simply go to chapter 1, open those pages, and you will see that I am more or less following the chapter section by section. So whether you look at these notes or you look at Discuss textbook will not make much of a difference. But in some places I will be skipping some portions so that you can immediately figure out. So what we will start in the very beginning, what we will start with is a very simple financial market. What is this market? This is called a single period securities market. There are 2 time points, 0 and 1. Even though I call it a single period, this will become clear as we go along. Because at time 0, which is the initial time point, all investments are made, all decisions are taken. So this is the only interesting period where you can do something. So at date 0, you make your investments or you take all the decisions. On day 1, the state of nature is realized. We were talking about that last day, that there is uncertainty involved and there are some possible states of nature. I don't know which one will be realized tomorrow. So that tomorrow is day 1, where the state of nature is realized and accordingly you get back a value on your investment. The value is definitely dependent on the state of nature and you consume it. So that's the end of the world. So on day 0, you take the decision. That's it. On day 1, based on your decision and the state of nature, a value will be realized for you, for your investment, and you consume it. So day 1 is a passive day where you get whatever you get, you consume. That's all. But day 0 is the decision making day, and that's why this is called a single period securities market. Notation, states of nature again. So this is just like our first year probability course. So we look at this capital omega, which is the list of the states of nature, and we start with a very simple structure. So it's a finite state situation to begin with. So I have capital K many states of nature, the omega 1, omega 2 up to omega k. One of them will be realized on date 1, and there is uncertainty about it in day 0, and that uncertainty is quantified by this probability assignment on omega, which is here, P1, P2, P2. So this is a basic discrete probability model. So what we really need, what is our data? Our data is a listing of the states of nature, possible states of nature, and the corresponding probability mass function. What are the processes that go on along with this? There is a bank process. And as I said, we keep assuming that bank is completely riskless. There is no uncertainty with regard to bank's return. So if I put 1 rupee in bank on day 0, I will get back 1 plus R amount on day 1. So B0 is bank investment today, which we standardize at rupee 1, and B1 is the net we get, which is the principal 1 plus the interest R. So R is the rate of interest. For the bank, R is fixed. R is non-stochastic. In case of bonds, remember that bonds still have a little bit of uncertainty involved because of the default probability. For bonds, we will keep assuming that the R is random. So when you talk about the return on bonds, we will consider it as a random variable. But when we talk about banks, we will consider it as a fixed constant. What about the other financial assets? So other financial assets are like stocks. So for now, we will talk about stocks or shares. Even though as we go along, we will understand that even if I cross out the term shares and replace it by some commodity or energy, it will still have the same connotation and the same mechanism as we are describing. So the same structure, same mathematical structure will also work when I am modeling commodity or energy or other, I mean, other than stock, other financial assets. Okay, so again, the price process has 2 time points. So S0 is the vector of stock prices today on day 0. And of course, this vector is completely known because on date 0, I know everything. S1 is the vector of all the stock prices tomorrow on day 1. And that is, of course, a random variable. So generically, we will call it S sub t. S sub t is S1t to S capital NT, as you can see here. Of course, at t equal to 0, it is completely known. T equal to 1 is where the uncertainty lies. S1 is a random variable. And that's the complete market that we are describing. So we have a single bank, B, and we have capital in many stocks, S1 to Sn, and their price process as described here. What is a trading strategy? So obviously we are talking about buying and selling, and this is in financial language called trading. So our trading strategy would be, I start with a fixed amount of money on day 0. I want to put some of it in the bank, and I want to also optimally divide the rest of the amount into the capital in many stocks. So this is called a trading strategy, which is denoted by this vector H, and H is nothing but H0, H1 up to H capital N, which are called portfolio weights. So what fraction goes to the bank and what fraction goes into each of the stocks. In general, so this is something that you should remember from the very beginning, that in general, these are all fractions, because I am using a fixed amount of money and splitting it up into different things. So they should all be a fraction and add up to 1. But there are exceptions. So we will have situations later on, not initially, we will have situations where you are also allowed to have a negative weight in some of the stocks. So HI can be negative for some I. Or you will be allowed to take a loan from the bank. So instead of depositing money in the bank, if you take a loan from the bank, that means H0 is negative. So again, initially we will assume that all the H's are between 0 and 1, so they are positive. So there is no short selling, no loan taking, etc. But later on we will slowly introduce them and see how the models change. So for now, we are working with this positivity restriction.
Sir,
Yes.
sir, what is meant by portfolio?
Portfolio is this combination. So in our statistics term, portfolio is basically a linear combination of stocks.
Okay.
Only stocks?
Sorry?
Sir, only stocks?
Right now we only have a bank and stocks, nothing else.
Okay.
Right now we are living in a very simple world where there is a single bank and capital in many stocks. As I said, you can substitute the term stock by other things, but that we will go to later. Okay, so this is your portfolio value. So now if you look at this value process here, the term portfolio will be clearer. So what is happening here is, you have put some money in the bank. The value of that amount will be H0 times BT, which is exactly H0 today because B0 is 1, and which is exactly H0 into 1 plus R tomorrow because B1 is 1 plus R. And the remaining money goes into the stocks. So HN SNT summation over small n. Again, at t equal to 0, this is perfectly known, but at t equal to 1, this is a random variable. And this is basically your portfolio. Is it okay? Is it okay?
Okay, sir.
Yes, sir.
Yeah, yeah. Sometimes it would help me if you respond because I cannot see your faces. This is not a real classroom. I don't get to see you. So please make yourself heard. Okay. It helps me to understand that you are with me and I am making sense. Okay, so using the value process, we define the gain process. So gain is what extra I get tomorrow starting with today's money. And of course, that extra is a random variable, certainly. That is defined as V1 minus V0. So gain is V1 minus V0, which is nothing but, if you just do the arithmetic, it is H0 times R, that is the gain from bank. That is a sure short, certain thing. And this is the notation for the gain in the stock price. So delta Sn is my notation for Sn1 minus Sn0. And this is certainly a random variable because Sn1 is random. So my gain from stocks is then summation over Hn delta Sn. And most of our financial maths will center around this quantity, the gain, because this is what is important for us. All right?
Sir,
Yes.
do we consider the HIs to be random variables or
No,
there's some parameter value?
The HNs are the weights which we are deciding on day 0. As I said, all decisions are taken on day 0.
Okay, sir. Oh,
So HNs are like our variables of choice. So we will do some optimization exercise. We will actually do the optimization later, usual first order condition, etc., etc., and optimally choose the H.
okay, sir.
This choice is done on day 0, then it is frozen. So on day 1, whatever I get, I have to take.
Okay, sir.
So bank, because bank is certain, bank is considered as a numeraire. So in economics, we have a term called numeraire. What does it mean? It means that I compare everything with respect to the bank's return. So if I say that a stock gives me more than R return, that is saying that I gain if I put it in the stock rather than keep it in the bank. So I get an advantage. And if it gives me less than R return, then I am losing. So basically R is like my no risk, no gain position. No gain, no loss position. Because R is the worst I can do. I can keep the money in the bank and I will surely get this R amount of return. So the objective would always be to see how much further up I can go from small r. So that's why bank is called the numeraire or the basis of comparison. So R is like our 0 line in day 1. In day 1, our 0 line is R. So how do
Sir, this is Shubhajyoti. Yeah.
Ah,
So I was thinking that when you are considering this gain, should we not consider the present value of V1 instead of V1 minus V0?
okay, yes. So actually that's what we will get to. That's what we will get to. So if you are already familiar with the present value concept, great. Even if you are not, I will not take the terminology, use the terminology, but we are going to the same point. So just hang on and we will get to the same point. Okay?
Okay, sir. Okay, sir.
So for me on day 1, 1 plus R is like the flat line, the 0th line, origin. So what can I do? I can make the calculations easier for me by dividing everything by 1 plus R. So if my return is more than 1 plus R, then after division it will be more than 1, which is a gain. And if it is less than 1 plus R, then it will be less than 1, then it's a loss. So actually what I should be comparing are these quantities called Sn star T. These are the standardized stock prices, discounted. In economics, these are called discounted stock prices, which is nothing but Sn divided by Bt. in our notation, it will simply be SN0 today and SN1 by 1 plus R on day 1. And if I do that division throughout, then the value process also becomes discounted. The gains process also becomes discounted. The new value process is called V star T. So we just put a star when we want to specify that it is a discounted process. So as I said, SN star is the discounted stock price. Similarly, V star is the discounted value, which will be given by this expression. It's very easy to understand why this expression will be like that. And the discounted gain will be this expression. Is that clear? It's very simple, just simple arithmetic.
Yes, sir.
Yes, sir.
So our main interest will be in trying to maximize G star. G star is something that we want to maximize. What is the advantage of this discounting? The advantage of this discounting is that then we can think of the bank as a very passive thing. It is doing nothing. Because after I divide by 1 plus R, the bank B1 star becomes 1 again. So I put 1 rupee in the bank and tomorrow I also get 1 rupee back after discount. So it is like bank is doing nothing. So I am comparing my performance against the bank which is doing nothing, passive. So that is why the discounting is helpful for calculations. A small example here. So these are again examples taken from Pliska. So suppose my state of nature, capital omega, has 3 points. Omega 1, omega 2, omega 3. There are 3 possible states of nature tomorrow. My rate of interest from the bank is 1/9. There is only one stock in the market. And the stock's price today is 5 rupees. Now, as there are 3 possible states of nature tomorrow, these are the 3 alternative stock prices tomorrow. So in state of nature 1, it will be 20/3. In omega 2, it will be 40/9. And in omega 3, it will be 30/9. And notice that this is a loss-making state. You see the price, initial price is 5. But if the third state of nature occurs, then you make a loss. But of course, we are not really interested in the S1 values. We are actually interested in the S1 star values because it is compared to the bank. So how do I calculate it? S1 star will be simply 20/3 divided by 10/9, which is 1 plus 1/9, which is 6. In omega 2, it will be similarly 4. And in omega 3, it will be similarly 3. So basically, I invest 5 rupees today in the stocks. Tomorrow, I may get 6, which is again after discounting, or 4 or 3. These two, see now these two are both loss-making states because in both omega 2 and omega 3, my bank is doing better.
Yes.
Yeah. So now, how is my portfolio valuation done? My portfolio valuation will be done with a V0 star, and the valuation will be H0 plus 5 H1 because 5 is the initial stock price here, and V1 star. So if you just go through the same arithmetic, it's very simple now. V1 star will be H0 plus H1 times S1 star, which actually I want to optimize. And the gain similarly will be given by H1 times S1 star minus 5. And now this is what we were talking about, that if I am in the first state of nature, my G star is actually H1. But if I am in the second or third state of nature, my G star is actually negative. Unless I am putting negative amount of money in the stock, which currently we are not allowed. Currently our H1 is between 0 and 1. So both the second and third state of nature is loss making. The first one is profitable. But I don't know. When I'm making the investment, I don't know. So I will have to rely on the corresponding probabilities. But this is how the calculation starts. So is this setup clear?
Yes.
Yes, sir.
So this is a very simple setup. Of course, in future examples, it will become slightly more complicated, but the basic principle is the same. And if you understand how the discounting happens and how the gain process is calculated, it's a simple arithmetic. The logic is very, very simple. All right, is it okay so far?
Yes, sir.
Yeah,
Yes, yes.
because I want to talk about the most important basic principle of the financial market now before I stop for the break. And that principle is called arbitrage. In fact, on the very first day, someone mentioned arbitrage. I don't remember who mentioned arbitrage. Somebody mentioned arbitrage who was doing an internship with Goldman Sachs.
No, sir, not me.
Not it. So somebody mentioned arbitrage.
Prakhar.
Sir, I mentioned.
Prakhar.
Prakhar, are you awake?
Yeah.
So can you explain arbitrage to us?
So basically, it's the inconsistencies in the market. Like,
What kind of
Okay.
inconsistency? It's a
like I can buy a stock at like certain market and then sell it immediately at a different. Like a stock has two different prices at different markets, so I can buy it at one place and sell it at a different place to gain a profit.
yes, but that is natural, isn't it? I could always do
Yeah,
that,
but
can't I?
Without any risk of loss.
Huh? Sorry, risk of?
Without any risk of loss, then it would be habit.
Without any risk of loss. Okay.
Huh.
So that is the important qualifier. So I make profit without any risk of loss. So is the distinction clear? I can always, identify profitable opportunities, but any profitable opportunity should come with a possibility of loss. There should be enough uncertainty involved so that my profitability is never certain. It's not certain. If my profitability becomes certain, that is not a very nice thing to happen. We will discuss why. And this kind of situations are these arbitrage situations. I think that's what Prakhar wanted to say, didn't you?
Yeah.
Yeah, okay. So let me just start this definition, then we'll take a break and continue after the break. So arbitrage, you have to understand arbitrage from a particular trading strategy situation where you make a profit all the time. So suppose you have this H tilde. So this is a formal definition. So let me just go through with that formal definition and then we can talk about the intuition. So I have a portfolio H hat, some portfolio H hat. If there exists another portfolio H tilde such that today both the portfolios have the same value. So at date 0, V hat and tilde are equal. Yes?
Hello?
Yes? What happened?
Sorry, sir, I was just checking my audio.
Your audio seems fine. Okay. So we were talking about dominant trading strategy. You're right. So I said that these two trading strategies, they give rise to portfolios which has the same value today, but for every state of nature tomorrow, V hat is larger than V tilde. So which means if I buy H hat today rather than H tilde, I will make a better gain for every state of nature. So which means my gain is certain. If I knew that, then I can use it in a different way. What I can do is I can sell units of H tilde and buy units of H hat. I can do that infinitely many times. So I can do it in arbitrarily large quantities. So what will happen is today I make zero amount of investment because for each unit of H hat, I have sold an H tilde. So there is no investment today. Whatever I get from selling H tilde, I use that to buy H hat. But what happens tomorrow? Tomorrow, I make a sure gain because in every state of nature, what I make is V hat minus V tilde. Is this clear? Is this clear to everybody?
Yes, sir.
So which means zero investment today, but sure profit tomorrow. This kind
Sir,
of,
how are you selling this again? I didn't understand that.
okay, so I said that I have two alternative portfolios. They have the same value today. So if I buy one of them and sell the other one, there is no cost involved.
Okay.
There is no cost because they have the same price. I sell one of them, buy the other. But these portfolios are such that tomorrow one of them gives me better value than the other in all states of nature. In every state of nature, hat gives me more than tilde.
Okay, so we're buying and selling in the same state of time.
Buying and selling, sorry?
We're buying and selling in the same time, like
At the same time.
either
Yes.
zero.
Buying and selling, see, all decisions are taken on day zero. So all the buying and selling is happening simultaneously on day zero.
Okay.
Huh? Day one, I cannot do anything. Day one is only for consumption. But I have created such a situation that on day one, I am going to make a profit in every state of nature. Because
Okay, how is the profit made? By selling?
I am selling tilde and buying hat.
Okay, okay.
I keep selling tilde and buying hat as many amounts as possible on day zero. One shot. On day zero, 1 crore of tilde sold, 1 crore of hat bought. That means tomorrow, whatever be the state of nature, I make a profit.
Okay, okay.
And this is a profit with zero investment. I make no investment, but I make a sure profit. And this is what I am saying is a bad situation or an arbitrage possibility, which we normally don't like. This is also called a free lunch. I think Srijit asked this question in some other context last week. So this is the financial free lunch. I don't pay anything. Yes.
Sir,
yes.
Why is it bad?
I will explain why is it bad. If you think about it, you will figure it out yourself, certainly, but we will also discuss why is it bad. So let me talk about free lunch. So the result is that if I look at the difference of these two portfolios as a new portfolio H, is the difference between H hat and H tilde, then this portfolio is called a free lunch portfolio. Because this portfolio has zero cost today. So if I want to set up this portfolio, I don't have to spend any money. But tomorrow, I will surely make a profit. That's why it's a free lunch. I get something for nothing. All right? Something for nothing is okay?
Yes, sir.
Now I
Yes, sir.
think probably you also understand why this is bad. But yeah, if you have questions, if you have any question, ask me, or we will take the break. So tell me. Okay then, so let us take a break and we will start at 12 o'clock. All right.
Okay.
So we were discussing arbitrage. So let me share my screen again. So we were in this part here, we are talking about a dominant trading strategy which gives rise to something called the free lunch. And this is a very simple extension of this result. That's the second result here. That if there is a dominant trading strategy like H hat, that is equivalent to saying that I can create a portfolio which has negative price today, which means if I want to buy something, I also get money for it. So I get the portfolio and some money, as well as I do not make any loss tomorrow. So H minus is a portfolio such that the price today is negative and the outcomes are all non-negative tomorrow. The proof is actually very simple. Can you all see how this works out? So I have just written a short reasoning is written here. It's very easy. So we started out with a dominant trading strategy with a strictly positive gain, right? So H hat minus H tilde had zero price today and strictly positive gain in its state of nature tomorrow. So if all the gain values are strictly positive tomorrow, I can simply look at the minimum of them. Whatever is the minimum gain tomorrow, that's a positive number. Now I subtract this minimum number from the value difference today and also subtract the same minimum value from each of the other gains tomorrow. So what will happen is today's price will become negative because it was 0 to begin with, and then I subtract something. So today's price will become negative. And tomorrow's gains will all be non-negative. The lowest one will be exactly 0, but the other values will be positive. So what am I saying? I am saying that it is possible to have a portfolio for which I get money today and also get money tomorrow. So on both days I get paid for having something. And that is surely illogical. That should not be allowed to happen. Right? And typically this will have many other bad consequences. So that is why the existence of such a free lunch in any market is a bad thing. And in financial literature, this situation is called illogical pricing. Illogical pricing because if I get paid for something today and also get paid for it tomorrow, so I do not need to invest anything at all, I get paid on both days, that is definitely illogical. So is that okay? Is that clear with all of you? That this is an illogical situation to have?
Yes.
So this is something that we do not want to happen. We do not want to have such a thing exist in the market. So we should not have arbitrage opportunities. We want to rule out arbitrage opportunities, and we want to rule out free lunch. Now, how can we make sure that such a thing will not exist? So the first important result in this line is this statement that if the pricing is logically consistent, which means there is no free lunch, that would mean that I must have something called a linear pricing measure. So we are going to define this linear pricing measure, this object. So if a linear pricing measure exists, then pricing will be logically consistent. So this is something that we want to show. Now, what is a linear pricing measure? A linear pricing measure is simply a vector pi over all the states of nature, pi omega 1 to pi omega k, where each of the entries are non-negative. Okay, each of the entries are non-negative, such that today's value V0 star is a linear combination of tomorrow's possible values, and the weightage are given by this pi vector. So V0 star must equal pi omega V1 star omega, sum over all the omegas. So this is called a linear pricing measure, which means that today's price is essentially a linear combination of tomorrow's possibilities. So this I can rewrite in terms of my portfolio calculation using our expressions for V1 and V0. So I can say that V0, which is H0 plus summation over Hn Sn star 0, this must be equal to sum over omega pi omega times V1, which is H0, V1 star, which is again H0 plus summation over Hn Sn star 1. So is this clear? So a linear pricing measure is this from vector pi, so that V0 star equals summation pi omega V1 star omega, which I can write out in terms of the stock prices in equation 1.6 here. That is clear, correct? And is this also clear? This is a very simple consequence, that this also implies that pi is actually a probability vector. Is that clear to all of you?
Yes, sir.
Is that clear to all of you, or anyone has any doubt here? This is again a very simple consequence. So just in case anyone has a doubt, just ask.
Sir, previously we had these P of omegas, those probability vectors, and now we have this pi. So these are two different objects.
These are two different objects. P is the natural probability.
Okay.
So the notation that we started out with is P is the natural probability assigned to each of the states of nature here. But pi is something different, because pi is actually coming out of an equation like 1.6.
Yes, so if you just consider this 1.6, so the right hand side is basically the expected value of tomorrow's portfolio. So this is going to be my price. So should not this expectation be calculated on based on those P vectors?
No. That's why we have two different sets of symbols, and we will actually see how they connect each other. They are not the same. They are not the same. So that's why. So your question is a very relevant one. First of all, why do I need two different vectors, 10 pi? And secondly, this expectation should go back to P, but no. We will see where and why pi is different from P. That is actually a very important issue in financial mathematics. So there is some noise here. I don't understand why. Yeah, okay, this is gone. So if this statement is clear that summation pi omega is equal to 1, which is pi is a probability, then we will continue. And then you can also see that if I can specialize to each single stock, which means I specialize in portfolios with only a single stock, then I also have this relation that Sn star 0 must also equal summation pi omega Sn star 1. So what I do is I take Hn equal to 1 and all the other H to be 0. Then 1.6 specializes to 1.7. So this is a linear pricing measure. And then we say that if there is a linear pricing measure, price will be logically consistent. That is also clear because if V0 star and V1 star are related by 1.6, then I cannot have a situation like this result, where V0 is negative, but V1 is non-negative for each state of nature tomorrow. These two cannot happen together if I have the linear pricing measure. Okay, again, that's straightforward, the simple arithmetic. But this has got very important implication for our model, which we will see. So if I have this linear pricing measure, which is in this here, 1.6, then I say that each claim means each portfolio has a unique price. Why is a unique price? Because I say that pi is well defined, uniquely defined. And if I have all the values, possible values tomorrow, then today's price is a direct calculation from tomorrow's values, summation pi V1. So the price will be unique. So I cannot offer two different prices for the same thing. And I also immediately have the consequence that if H hat gives me better payoff than H tilde for all omega, so which means V1 hat is more than V1 tilde for all omega, then it must be the case that V0 hat must be bigger than V0 tilde, simply because of the linear combination rule. Because now V0 is a convex combination of the V1 values. So if one is greater in all omega, then the other must be greater. So free lunch is automatically pulled. So again, let us look at some of the consequences of this thing. So this is a straightforward result that if pi is a linear pricing measure, then that statement is equivalent to saying that pi must be a probability, which we have shown, and V0 star is actually the expectation of V1 star under the probability. It is important to mention under the probability pi here, because as Subhrajyoti already pointed out, that we started out with a natural probability allocation of P. So if I say expectation, there is a scope for confusion that under what probability am I calculating the expectation. So this expectation here in this result is under the linear pricing measure. And it is as yet not known, but we will make it clear that the expectation under P is a different object.
So in that P, is it over the 0th day?
No, 0th day is certain. I know everything about today. The only uncertainty is about tomorrow, but I have to take my decisions today. Uncertainty is about tomorrow, but I have a probability distribution about it. Based on that, I have to take my decision today. I have to optimize whatever I want to optimize and take my decision on basis. Okay, so here is a formal proof of this statement. Again, this statement is quite intuitive. The second result here, that if there is a, yes.
Sir, your voice is breaking.
My voice is breaking. It has become cloudy, so. Am I clear now?
No, sir.
No. So I'm just trying to do an alternative, let me see, because there might be internet issues now. So can you not hear me at all, or is it just coming up in?
Now it is fine.
It's better now.
Fine.
Yeah.
Now?
It's much better now.
Oh, great. Thank you. So then let us continue. Lovely. All right. So this result, the second result that I wanted to discuss now at this point is, if there is a linear pricing measure, then that is equivalent to the statement that there does not exist a dominant trading strategy. So these two are equivalent. So if there is a linear pricing measure, there cannot be a dominant trading strategy. And if there are no dominant trading strategies, there will be a linear pricing measure. And there are many ways of proving this: intuitively, geometrically, algebraically, etc. What I will be using here is what Pliska has done. Pliska has formulated this problem as a linear programming problem. So it's an application of the typical linear programming that you have learned sometime. And there you have a result called a duality theorem. Do all of you remember duality theorem?
Yes, sir.
Yeah.
Yes, sir.
So the duality theorem is used here. So let us look at the proof. It's actually quite simple. So let us define a vector Z with all the day zero payoffs. So I have the n stocks first and then the bank. The bank comes at the bottom. And I define a script Z matrix with all the possible payoffs tomorrow. Okay. So there are k many columns, which are the states of nature, and there are n+1 rows representing each of the assets, n stocks and one bank. And because we are talking about discounted quantities, tomorrow's bank is also 1, because I divide everything by 1 plus r. So B1 also becomes 1. This is the convention we have been using. So I have this vector and I have this matrix. There, let us start with existence of the linear pricing measure. So existence of linear pricing measure implies there exists a solution to this LP problem. It's a trivial LP problem, but it has a solution. What is the trivial LP problem? I maximize 0 times pi, so that is identical 0, such that Z pi is equal to Z. So Z pi equal to Z is essentially the linear pricing measure definition. So this has a solution because there is a linear pricing measure. This is a solution. And this is an equality, but to maintain the convention, we will consider this as a less than or equal to, because I am maximizing. What is the dual problem to this one? The dual problem will be there exists a vector H with n+1 entities, and my dual problem will be minimizing H prime Z, that's the dual, such that H prime script Z is greater than or equal to 0. So I have a non-negative vector H with n+1 entities, and I am minimizing H prime Z such that H prime script Z is non-negative. That's the dual. Okay. So what is the intuition here? The intuition is that the tomorrow's value is given by H prime Z. So when I am minimizing H prime vector Z, this cannot be negative. This is because of the property of the linear pricing measure that I cannot have a free lunch. So if tomorrow's value is non-negative, then today's price cannot be negative. So the solution to this dual will exist, and the optimal value can be h prime z equal to 0. That's the minimum possible. It cannot be negative, as you already mentioned. Now, let us interpret this H as a trading strategy. So if I think of H as a trading strategy, then the statement we are making is the following. H prime z is 0, which means V0 star is 0, and H prime script z is non-negative, means V1 star omega is non-negative for each omega. So what I have proved is, if I have a portfolio which has non-negative payoffs tomorrow, then the price today cannot be negative. The minimum possible is 0, which means I'm saying that there does not exist a trading strategy H such that the price today is negative, but the payoffs tomorrow are all non-negative. So here what I am using is the earlier result, this one. I'm using this one. So today's price negative, tomorrow's gains are all non-negative. So this is I am using as an equivalent to no dominant trading strategy. So starting from the existence of a linear pricing measure through the dual, I can say that there cannot exist a dominant trading strategy. Okay, and since this is the minimizing strategy, so I will not have anything like that. So that gives me the one direction of the proof. And now if you just look at this, we can reverse arguments and also show the other way implication in the same manner. So is that proof clear? Because I wanted to prove an equivalent statement, I have shown the first half, but I am saying that I can easily reverse steps and show the other side. Is that clear? So I can again similarly construct a linear pricing measure from this. Because the other way would be that if I don't have a dominant trading strategy, then I should be able to construct a linear pricing measure, which would be the expectation kind of operation. Okay. So that's our result, and this is one way of proving it using linear programming. That the bad situation that we wanted to rule out was free lunch. Free lunch is an illogical situation, we want to rule it out. And we have now shown that ruling out free lunch situations or ruling out dominant trading strategies is same as showing that there is a linear pricing measure. If there exists a linear pricing measure, then the bad situation is ruled out, and vice versa. All right. So now let us move on with that knowledge and let us formally make the law of one price statement. So this is a consequence of this result above, and it's a very important statement. So we call it the law of one price. What is the law of one price? It is again very simple, that if I have two portfolios which has the same outcomes tomorrow, so I have two portfolios, they have the same outcome tomorrow, then their price today must be equal. Or in other words, this statement is saying there does not exist two portfolios with the same outcome tomorrow, but one of them is more expensive than the other. This is the law of one price. Okay. All right, is this okay? This statement, is it clear?
Yes, sir.
So then there is a result. This result is slightly counterintuitive because we thought that these things should all go together. They should be like equivalent statements, but this result says that equivalence is not yet there. We don't have two-way implication. This result says that if there are no dominant trading strategies, then law of one price will hold. So one-way implication is fine, but converse is not necessarily true. So how do I show this result? Basically, the first part where I say that there are no dominant trading strategies, then I can construct a linear pricing measure, and that will tell me that law of one price will hold. So the linear pricing measure will actually imply the equality. But how do I show that the converse is not necessarily true? So obviously we provide counter examples. So this is a counter example here. And obviously we will see later on that these are artificial counter examples. So this counter example says that I will put a situation where there are two states of nature, omega 1, omega 2. The stock price is equal in both states of nature, 12. The rate of interest is 1, which means basically V1 is constant on omega. In both states of nature, I have the same stock price. So V1 becomes a constant on omega. And for any scalar lambda, take any scalar lambda, there exist infinitely many trading strategies such that V1 equal to lambda, but they can have different price on day 0. Because I have this equality of values tomorrow, I can have different combinations with different day 0 prices, but they will give rise to the same value tomorrow because the stock price is a constant, V1 is a constant tomorrow. So this is definitely an artificial situation, but as yet we have said nothing to rule out such artificial situations. We will do this later on. But in this artificial situation, I can say that even though law of one price holds, I still may have dominant trading strategies and products. And this is also an exercise in chapter 1. So when you go to the chapter 1 exercises, there is an exercise which explicitly asks you to do this. Okay. So now let us talk more about the arbitrage opportunities. So arbitrage opportunities are like things that we want to rule out. Our objective is to try and rule out arbitrage opportunities. So we want to understand them very clearly. So what is an arbitrage opportunity? In terms of the value function V, an arbitrage opportunity is a trading strategy which has 0 value today, which means no investment, non-negative payoffs tomorrow at all states of nature, which means no risk, and a strictly positive expected payoff tomorrow. So which means I have a possibility of profit. So not all of these are 0, at least one of them must be strictly positive. Expectation is strictly positive. So I pay nothing today, but I expect to get something strictly positive tomorrow. That is one way of stating the arbitrage opportunity. Result, immediate consequence. So if a dominant trading strategy exists, then there will exist arbitrage opportunity. Again, converse is not necessarily true. So again, one way of proving it is direct computation. For the converse, you will need a counter example, and that counter example is again an exercise 1.6. So that is something that you should look at, how to create such counter examples. And we will see that to create such counter examples, we will have to use some artificial situation, but it can be created. So that is one definition of arbitrage opportunity. Equivalent alternative definition is in terms of discounted values, which says V0 star is 0, V1 star is non-negative, and expectation of V1 star is strictly positive. These two are the same because I just divide by V1 in each of the quantities. And the third alternative is in terms of the gain, which says G star is non-negative and expectation of G star is strictly positive. So these are equivalent statements, and we use them depending on which expression is convenient for us to use in any given situation, whether we are more comfortable working with V or V star or G star. Okay, is this okay so far?
Yes, sir.
So our
Yes.
discussion of these different requirements of the market, no dominant trading strategies, no arbitrage opportunity, law of one price, these things I summarize in this diagram. You see, this diagram follows from the earlier two results. So we had these statements here that if there are no dominant trading strategy, then law of one price holds, but the converse is not necessarily true. So which means law of one price is a superset of no dominant trading strategy, which is in the first half. So this is law of one price, the biggest rectangle, and the second rectangle is no dominant trading strategy. The other result is, again, if dominant trading strategy exists, then there exists arbitrage opportunity. Converse is not necessarily true. So no arbitrage opportunity is again a subset of no dominant trading strategy. And for each of these strict inclusions, what you need to do is produce counter examples. So inclusion, the one way inclusion is direct constructive. The other way, non-inclusion, you have to show counter examples. So examples of situations here where no dominant trading strategy holds, but no arbitrage opportunity does not hold, or here where law of one price holds, but no dominant trading strategies does not hold. So that's our initial setting, that when we have law of one price, we have a linear pricing measure. So let me go back and recall the linear pricing measure. So linear pricing measure is a vector pi. This is a probability vector with non-negative elements. All are greater than or equal to 0, and it's a probability that we have shown. So with the linear pricing measure, in our simple setting, we have this set of results, these inclusions. But when we think about the financial market, ideally, we would want these to be strictly equal. The law of one price, no dominant trading strategy, and no arbitrage should be equivalent statements. But so far, we are able to create counter examples. So, what is the best way of closing this gap? So to do that, to close that gap, we define something called the risk neutral probability. So what is a risk neutral probability? It is a probability Q on omega. So now we take a new symbol Q. So from pi, we already had P, the usual probability assignment. We had pi, which is the linear pricing measure. Now we have Q, which we call the risk neutral probability. How is it defined? It is a strictly positive probability vector. So this is the difference. It's a strictly positive probability vector such that under the probability Q, expectation of delta Sn star is equal to 0 for each of the securities. Or in other words, for each of the securities, the expectation of Sn star 1 must be equal to Sn star 0. So if you think about the linear pricing measure, it is very similar to linear pricing measure, because with the linear pricing measure also we had similar kind of expectation connection. So again, if I go back to the linear pricing measure connection, you will see that here in 1.7, Sn star 0 was given by expectation of Sn star 1 under pi. This relationship 1.7. Now contrast it with the risk neutral probability requirement, which is equation 1.15. So I am writing these equation numbers here because they correspond to Pliska equation number. So if you are following the book, in the book, this is the equation 1.15. So it's the same expectation expression under Q, but how is Q different from pi? The only difference is each element of Q is strictly positive. So there are no zero probabilities on any state of region. This is an important distinction. Okay, so we will work with that. Okay, is this clear so far? So from pi we are moving on to Q with a certain distinction, and we want to see how it changes the consequences. So let us work with the risk neutral probability, strictly positive, and expectation of delta Sn star equal to 0. Now, this risk neutral probability is also called an equivalent martingale measure. Why? We will clarify this later on, because we have not yet defined what is a martingale. By the way, this has a spelling mistake. This will be G-A-L-E. Okay, martingale, G-A-L-E. So whoever took those notes, it's the last batch, missed an A. So first of all, let us look at a simple example. So for now, let us think of this expectation equal to 0 to be the martingale condition, which we will clarify later, which in economic terms mean under this probability Q, we do not expect to make any profit after discounting. It's a very strange condition because we actually learn quantitative finance to make money, but what we are instead learning is what are the conditions for not making any money. But we will come to that point, okay? Because we are trying to define a market which is quite smart, quite efficient. And in an efficient market, there are certain things we want to rule out, like arbitrage opportunities, like free lunch, okay? Dominant trading strategies and all that. And as a consequence, we also see that we are not supposed to make profits, but we will see. So, result. Now, this is the first equivalent statement which helps us. There are no arbitrage opportunities even only if there exists a risk neutral probability. So, what do I have? In this box, when I had law of one price, I had no dominant trading strategies as a subset of that, strict subset. But when I am changing my probability to the risk neutral probability, I say that having a risk neutral probability is equivalent to no arbitrage opportunities. So now it is equivalent. So both its OA implications are true. So the sets are identical. That means I have closed the gap, which means the counter example that we needed earlier to show, the counter example that we needed in this space, in this gap here, can no longer work. So that means the counter example that worked here needed one of the probabilities to be 0, one of the pi values to be 0. Now that we have ruled out any 0 probability, Q is a strictly positive probability vector, that counter example is ruled out. So we have this equivalent statement. Having a risk neutral probability is same as ruling out arbitrage opportunities. Again, let us look at an example. Similar kind of example from earlier. You have a 1/9 rate of interest. There are 3 states of nature with the same payoffs as earlier. S0 is 5. So I have 6, 4, and 3 as the discounted stock prices tomorrow. We did this before. And delta S1 star will be 1, -1, -2. Now, because we have this condition that delta Sn star expectation has to be 0 under Q, for this stock S1, I have the condition that Q1 minus Q2 minus 2 Q3 must be 0. Correct? This is the expectation. There is only one stock, so the expectation must be 0. So that is a equation involving the Q probabilities, which means Q1 must be equal to Q2 plus 2Q3. And of course, Q is a probability, so the sum of the 3 elements must be 1. So can I get a solution here? Is this a feasible set of restrictions? We can see that yes, it is. Q has to be of this form: 1 plus k by 2, 1 minus 3k by 2, and k, where k has to be suitably restricted so that all these elements are strictly positive. One example is 3 by 5, 1 by 5, 1 by 5. So for any solution of this form, if I choose a Q like that, it will work as the risk neutral probability in this situation. So now you see the important distinction between the risk neutral probability or the linear pricing measure with the natural probability. So this is the question Subhrajyoti asked earlier, that why do we need two different things? The original probability allocation was exogenous. So it was done by looking at the situation, but not looking at the prices of stocks. So it was not linked to the price of stocks. So it was a natural probability. That is why it is also called subjective probability, because it will depend on any trader's perception. My perception may be different from yours, so my probability allocation can also be different from yours. It's a subjective choice after all. But what we see here now is that the Q probability is not a subjective allocation. It is strictly linked with the changes in the stock price. So Q probability is not a natural allocation. Q probability is an outcome from the stock market. So it is not a natural subjective probability. So this risk neutral probability or equivalent martingale measure, whichever name you want to use, is a consequence of the stock price structure. Is this clear to all of you? Because I am suddenly talking about two different kinds of probability. One is the natural probability, the way you usually talk about probability, but the other one is an outcome of the stock price structure. So it is an outcome of the system, not an input. So is this distinction clear?
Yes.
So Subhrajyoti, does this answer your question or confuses it more?
It does answer.
This is being implemented in the market, right?
This is being implemented through the market, yes.
To avoid arbitrage.
To avoid arbitrage. So this risk neutral probability is the one that we are going to use for a long time now. And here, of course, it's not a unique probability, of course. You can see that there are multiple such candidates of this form, and there are many such. Okay. As long as K is, I think, between 0 and 1/3, strictly between 0 and 1/3, it will be fine. So basically, what are we trying? If you think of it as a vector matrix problem, we look at this delta Sn star vector. For each of the stock Sn, nth stock, I have a delta Sn star vector. So I want an orthogonal vector to that. That orthogonal vector is my candidate Q, so that Q prime delta Sn star is 0. So I got disconnected. Can you hear me now again?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yeah, I got disconnected. So let me just go back to my screen sharing and something went wrong. So can you see my screen again?
Yes, sir.
Yeah,
No,
can
No, sir. No, sir.
Not the screen. We can see you.
you can see me. That's not important. Can you see my screen?
Yes.
Yes.
Yeah, great. And is it still recording?
Yes.
Yeah, okay, good. So somebody just keep an eye on that, because if I am in trouble, then I will need help. All right. So with that risk neutral probability, what we are really doing is finding orthogonal vectors. So if I have capital N many stocks, then I will basically need a vector which is orthogonal to all the delta Sn stars. Okay.
So how is this implemented? I'm not just able to picture.
Yeah, we will see that. We will actually.
So
we will see how it is implemented precisely. So just bear with me a little bit more. We will get there. We will get there. So let us look at one more example before we move on, because that will give you a flavor of exactly the way we are going in terms of the implementation. Okay. So now I have two stocks. So let us make it a little bit more realistic. I have two stocks here. This is the corresponding price today. These are the possible values tomorrow. There are three states of nature, same rate of interest. So I do this discounting calculations. So I have S1 star and I have S2 star in these two rows. So I also have the gains delta S1 and delta S2 here. Okay. Now, as soon as you see delta S2 star, as soon as you see delta S2 star, you can immediately conclude that a Q will not exist.
Yeah.
Q cannot exist because all the three entries are negative here. So it is not necessary that a Q will exist all the time. In the earlier example, we had infinitely many such. All Qs of this form would have worked. But now, even with two stocks, I immediately have a situation where a Q will not exist at all. So this is something that we need to fix. We need to have a clear-cut statement, some clear-cut theorem, which will say under what conditions and in what structure we will have such a Q. And of course, for that, we will talk about a theorem. So what is my theorem? What is the theorem? So the theorem is there are no arbitrage opportunities if and only if there exists a risk neutral probability. This one we wanted to formally show, and this proof is a constructive proof. So again, in this proof we are going to use explicit vector matrix type arguments. It can be proved in many different ways, but this way is more constructive so that the implementation part becomes clear, because the implementation is going to be important going forward. So when we make a formal proof, we also try to make it more implementation friendly. Okay, so this is our proof, and what we are going to do is we are going to define this orthogonal operation in a suitable manner. Okay, so let us define a set W first, which is all the vectors in Rk. So K is the number of states of nature, the dimension of capital omega. All the vectors which can represent a G star for some trading strategy. So it's like, look at all the possible trading strategies, calculate their corresponding gain, G star, discounted gain, collect them in the set W. That is my set W. And then define the W orthogonal set. What is W orthogonal set? It is all the vectors in Rk which are orthogonal to X for all X in W. So basically collect all those vectors in Rk which are orthogonal to all the elements in W. That's the orthogonal set to W. So W and W orthogonal. Now define another set A, again with elements in Rk, where elements are all non-negative and at least one of them strictly positive. So it's a non-zero vector, not all of them are zero and they are non-negative. So I will start with these three sets. Now first notice that arbitrage opportunity is equivalent to having an intersection between W and A. Is that clear? Because W is the gain vector set. So if gain vector has all non-negative entities, then that becomes a free lunch construction. So there will be arbitrage opportunity. So I say that arbitrage opportunity in this setup is equivalent to W and A having a non-empty intersection. Is that clear? Is this first part clear? Just think about it.
Yes, yes, sir.
Okay. So I start with the statement that W and A are disjoint. W intersection A is null. So if W and A have no intersection, then I make the following statement. Now this is a geometrical statement. I make the statement that there exists a ray in W orthogonal along which every component of every point not at origin is strictly positive. So it is like this picture here in 2 dimensions. I am saying that there will be a ray like this in W orthogonal where except from this origin point which is 0, 0, at all other points the coordinates are strictly positive. Is that clear? Because W and A are disjoint, I am basically saying that then I can have some common point with W orthogonal, and I am claiming that there will be a ray like that in W orthogonal. So I wanted non-negative, but there can be at least one ray which has strictly positive components. So how does that work? It works in the following way, that if these two are disjoint, then if there is an x equal to G star which is actually non-positive, so which means it's either 0 or negative, then there will be an orthogonal vector V, so that V prime G star is 0. And then I can choose a V to be strictly positive, which means something like this here, all elements to be strictly positive. Can you see that?
Yes.
So just check carefully. Maybe if you have pen and paper, try to draw this picture and argue it with that picture. I am giving a very geometric proof here, but because I wanted it to be a constructive one, a geometric argument is more useful for us.
So here this x equals to G star less than equal to 0. This means that some elements may be less than 0, right?
Yeah, maybe less than 0. In fact, see, the way we have defined a no arbitrage opportunity, in G star there must be some negative elements. They cannot be all positive, otherwise they will become members of A. You see, A is precisely all the non-negative element vectors, A here. And A cannot have an intersection with W, that we have already argued. So that's where we are coming from. Then the next step is actually, I have another picture drawn. Let me find it out. I drew a picture which I want to show you. I don't know whether it is coming. It's not coming.
So close it again and open it.
Yeah, close it.
Close it again and open it.
So let me open it in some other software. Maybe open with. Some of the things may not work as well. This is good. Now all of you can see this picture, correct?
Yes, sir.
So what I'm saying is, first we constructed this ray. This red line is the ray here, which we constructed, where elements are strictly positive. Now I say that if I have such a ray, then on that ray there must be one point where the sum of the elements will be equal to 1. So basically what I do is I intersect it with the line x plus y equal to 1. There will be some intersection. And basically this is my candidate for Q. This intersection is my candidate for Q, which has all strictly positive elements and the sum is 1. So the picture obviously is in only 2 dimensions. I cannot do more than that. But you can think of this in the actual k dimension space where k is more than 2. So that's the argument here. So what I am doing is I am saying that I have this strictly positive ray, and in particular there exists a point on the ray whose components sum to 1. So what do? I collect such points, call them P plus, a new set where the sum of the components equals 1 and each of the components is strictly positive. So it's a strictly positive probability vector. So these are my candidates for Q. So then what I have shown is the following, that if W and A are disjoint, so I started out with this statement, W and A are disjoint. I have shown then W orthogonal and P plus will have an intersection because these points are also in W orthogonal. So W intersection and P plus is non-empty. And we also know that delta Sn star belongs to W. So if delta Sn star belongs to W, then that is equivalent to saying that delta Sn star times any element in P plus will be 0. Which means this set that we have identified, this non-empty set, is essentially the set of all the risk neutral probabilities. Because it is constructed in that way. It is constructed by this x prime y equal to 0 for all x in W. So these are all the risk neutral probabilities in our setup. And we call this set as capital N. So the final statement is, what have we done is, so no arbitrage opportunity is equivalent to saying this set is empty. That is equivalent to saying this set is non-empty. And that is equivalent to saying there exists risk neutral probability. Of course, it can be many risk neutral probabilities, but so far we are only interested in existence. So there could be many such. In fact, in this example, we could have infinitely many, but we don't have a problem with that. In the first example, remember, in the first example, all Q vectors of this form are allowed. So there are infinitely many of them. So that is our result. And you see that all the steps that we have used in this proof are actually reversible. So the equivalence is established. So is that clear? So we made a statement here, this result. No arbitrage opportunity is equivalent to having risk neutral probability. And then we showed a couple of examples, one positive example and one negative example. And using those examples actually as motivation, this is a constructive proof here, because later on we will actually do computations. And this constructive proof gives us the equivalence, but it also says that there might be many risk neutral probabilities. So that's where we will stop today. And if you have questions, ask me. Are there questions? Can you hear me?
Yes, sir.
So if there are questions, ask me, or you can think about it and we can get back to this on Wednesday. Okay, so I guess we are all ready for lunch. So all right, so we'll stop today. And Wednesday 10:30. So remember that I'm going to start my class at 10:30 rather than 11 o'clock. It's easier for me. Okay.
Yes.
All right.